Welcome, everyone. Let's get started. Today, we are analyzing a terrifying breakthrough in cybersecurity, how Anthropic's Claude Mythos autonomously bypassed modern web browser sandboxes using a highly complex technique known as a JIT Heap Spray. Let's begin with the what. Claude Mythos Preview is an unreleased frontier model developed by Anthropic that has radically changed our understanding of AI offensive security capabilities. The basics of this achievement are staggering. Mythos was able to autonomously escape modern web browser sandboxes. Why is this so significant? Because modern browsers are the most heavily fortified consumer software in the world. They use layered sandboxes to prevent malicious JavaScript from touching your operating system. But how did Mythos beat this? It autonomously discovered and chained together 4 separate vulnerabilities, culminating in a highly complex technique called a JIT Heap Spray. In our deep dive today, we will unpack exactly how an AI agent orchestrated this, transforming a simple memory corruption bug into a weaponized sandbox escape. Looking at this high-level architecture diagram, we see the boundary layers Mythos had to penetrate. We start at the top with a malicious web page loading inside the browser renderer sandbox. Normally, the threat stops right there. But Mythos engineered an exploit chain using a JIT Heap Spray. This specific technique breaks the renderer boundary, leading to an OS sandbox escape and ultimately achieving full kernel access. It is a masterclass in dismantling defense-in-depth architecture. To understand the attack, we must first ask, what is JIT? Modern web browsers rely on just-in-time, or JIT, compilers. The basics are simple. Instead of slowly interpreting JavaScript, the browser compiles it into native machine code on the fly. Why do we do this? It makes web applications incredibly fast. However, how does this affect security? This dynamic compilation means the memory layout is constantly shifting and highly unpredictable. To counter attackers, browsers add JIT-specific hardening defenses, effectively randomizing where code lives. Bypassing this requires the attacker to build stable, primitive foundational actions like arbitrary memory reads and writes. Finding these in a dynamic JIT environment is extraordinarily difficult for humans, yet Mythos was able to discover them fully autonomously. This flowchart illustrates the defender's advantage in a modern browser. The JavaScript code enters the JIT compiler, which immediately applies memory randomization. This branches out into unpredictable machine code and specially hardened execution pages. The ultimate goal of these defenses, shown by the dotted line, is attacker confusion. The memory shifts so constantly that an attacker cannot reliably point their exploit to a malicious payload. Now we define the core technique. What is a JIT Heap Spray? It is an elite exploitation method used to defeat the memory randomization we just discussed. The basics involve forcing the browser's JIT compiler to generate massive amounts of highly predictable, executable machine code. Why do this? If an attacker cannot know exactly where their payload is hidden, they simply flood or spray the memory heap with thousands of copies of it. If they hijack the execution flow and jump to almost any random address, they will hit their malicious code. How did Mythos execute this? It utilized the arbitrary read and write primitives it discovered to carefully structure JavaScript arrays and objects, coercing the JIT engine into allocating specific, weaponized byte sequences. This step is critical. It occurs right after initial memory corruption, bridging the gap to full code execution. Take a look at this flowchart representing the browser's memory heap during an attack. Instead of a single, hard-to-find payload hidden among random data, the JIT Heap Spray floods the memory blocks. Notice how sprayed payloads 1, 2, and 3 dominate the available space. If a vulnerability allows the AI to redirect the system's execution pointer blindly into this region, the sheer density of the spray guarantees the execution hijack will succeed. Let's examine how Mythos actually performed during testing. What Anthropic discovered is that Mythos doesn't just flag bad code, it writes the functional exploit. The basics of their test involved challenging the AI to exploit known, patched vulnerabilities in Mozilla's Firefox 147 JavaScript engine. Why Firefox 147? It served as a perfect benchmark to compare Mythos against the previous model, Opus 4.6. How vast was the improvement? Opus 4.6 managed to produce a working JavaScript shell exploit only 2 times out of hundreds of attempts. But Mythos Preview autonomously developed working exploits 181 times, achieving a massive 72.4% success rate. In our deep dive, we see that Mythos doesn't just guess, it reasons. It reliably triages crash logs, identifies which bugs are most exploitable, and leverages distinct vulnerabilities to force reliable code execution. This visual comparison perfectly highlights the paradigm shift in AI offensive capabilities. On the top path, we see Claude Opus 4.6, registering just 2 successful exploits representing basic human-level triage. On the bottom path, highlighted in red, Claude Mythos preview towers over it with 181 successful exploits. This represents an evolutionary leap from an AI that occasionally gets lucky to an autonomous, superhuman exploitation factory. Our deep dive brings us to exploit chaining. What is it? It is the art of linking multiple separate bugs to achieve a catastrophic compromise. The basics here are terrifying. Mythos chained together 4 completely distinct vulnerabilities to drill all the way from a web page to the operating system kernel. Why is this necessary? Because modern browsers use defense in depth. If you hack the browser renderer, you are still trapped in an OS sandbox. You have no real power. How did Mythos solve this? Fully autonomously, it developed read/write primitives to bypass cross-origin policies, executed the JIT Heap Spray we discussed to get code execution, and then appended a local privilege escalation exploit to break out of the OS sandbox entirely. This sequence diagram maps the exact attack path of the 4 vulnerability chain. The malicious script starts by triggering a memory bug to gain read/write primitives within the JIT engine. Next, it executes the JIT Heap Spray to force predictable memory allocation. This grants code execution within the renderer sandbox. Finally, the AI agent deploys a local privilege escalation, or LP, escaping the sandbox and granting itself full kernel write access. The AI planned and executed every step autonomously. Let's look at the underlying logic with some conceptual code context. What does it actually look like to force a JIT compiler to allocate native memory? The basics involve creating massive arrays in JavaScript, often using floating point numbers. Why floats? Because JIT compilers highly optimize arrays of floats, storing them directly as contiguous raw bytes in memory for performance. How does the attack look? Look at the pseudocode on the slide. We create an array of 100,000 elements and fill it with a malicious float. The brilliance here is that this float isn't a real number. It is native machine code encoded as an IEEE 754 decimal value. Mythos autonomously calculated the exact floating point representations of its payload to smuggle raw CPU instructions past the JIT compiler and directly into the executable heap. This flowchart demystifies the float encoding trick. It starts with a harmless-looking JavaScript floating point number. Through standard IEEE 754 encoding, this becomes a precise binary hexadecimal value. The JIT optimization process unknowingly copies this binary straight into executable heap memory. When the AI forces the CPU to jump to this memory, the CPU misinterprets the data not as a number, but as a malicious CPU instruction. It is a brilliant exploitation of system architecture. To fully grasp this, let's explore a real-time, highly critical use case, the cross-origin bypass. What does this mean for an everyday user? Imagine a scenario where an unsuspecting victim visits a seemingly safe web page that hosts a malicious advertisement crafted by an AI like Mythos. Once the ad loads, the execution begins. The JIT spray triggers instantly in the background, granting the AI agent code execution. Mythos uses this to shatter the browser's cross-origin resource sharing policy. The impact is devastating. The script running on the malicious ad can now silently read session data, passwords, and balances from another open tab, like your bank's website. In Anthropic's deep dive, Mythos went even further, chaining this into a kernel write. This proves that simply viewing a web page without clicking or downloading anything could result in total machine takeover. Here is the real-time attack path visualized. The victim simply visits the malicious site. Immediately, the hidden ad triggers the JIT spray. This shatters the cross-origin policy, branching directly into a silent read of the user's active banking tab. The end result, highlighted in red, is stolen session data and financial compromise, all executing autonomously in milliseconds. To conclude, how do we defend against this? Recognizing the immense danger, Anthropic refused to release Mythos to the public. Instead, they launched Project Glasswing. The basics of this initiative involve granting restricted access to major tech consortiums. Why? To let defensive engineers hunt and patch these critical vulnerabilities before adversaries develop their own frontier models. How must we adapt? We must transition to machine-speed defense. You must integrate AI directly into your software development lifecycle to break your own code before you ship it. The window between discovery and exploitation has collapsed from months to minutes. To master these advanced security concepts, implement machine-speed defense, and accelerate your career, visit quicktechie.com. Access our premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Like, subscribe, and secure your future with QuickTechie today. Our final mind map visualizes the machine speed defense strategy. To combat tools like Mythos, organizations must embrace initiatives like Project Glasswing for proactive patching. They must shift left, integrating AI into the SDLC for automated triage. And fundamentally, they must adopt zero-trust principles, relying on hardware isolation and memory-safe languages to blunt the impact of automated exploitation.
To find related ebook and other material for this training course, go to quicktechie.com. Now you will see all the video courses are available here. So let's move to the ebooks. You can go here, ebooks, all AI related ebooks, like you are watching currently Mythos related training. That ebook would be uploaded under this section. You can download this ebook. PDF would be available, all 300-page PDF. So you just click on the download this entire ebook. You can download from this section. So whatever training you are currently listening, corresponding ebook would be available. We have thousands of ebooks available. Now, other than that, we have on video courses which you are watching right now. This also all AI related courses are available. Similarly, for all company related trainings are available, like Microsoft, you can find it here with their respective certification training modules. All exam simulators which would help you to get the certification preparation. Just refresh if you get this kind of error. Okay, so now you can see these are all certification preparation materials. Will also be click here to the NVIDIA certification preparation material. So you can see all NVIDIA certification preparation materials. Click on any of this and it would load the entire screen and you can launch the practice paper. So this is what you can see, that you can submit the answer. We have an audiobooks available. Okay, so for each section, and these are our alumni who can you can find out all alumni who are accessing our portal.